Assalamualaikum warahmatullahi wabarakatuh. My name is Wan Ahmad Izuhiman bin Muhammad Mahidi. My metric number is 1222715. So this is my project, which is optimizing car suspension systems using differential equations and Mathematica. Okay, now let's move to introductions. A car suspensions plays a vital role in ensuring both comfort and safety by maintaining tie contact with the road and absorbing shocks. Achieving a balance between ride quality and handling requires a combination of engineering and mathematics. This project focus on the mathematical modeling of suspensions system using Hooke's laws and second order differential equations. Modern adaptive suspension dynamically optimize performance, and computational tools like Mathematica help analyze and improve the system for smoother, safer ride. Okay, and this is a problem statement. Designing the perfect suspension system is challenging because it involves competing objective, comfort, and stability. For instance, passengers desire smooth rides, but the vehicle must maintain stable and responsive to the tiring. These challenges are compounded by factors like varying road conditions, evolving vehicle technologies, and different weight distributions. Moreover, traditional tuning methods for key parameters such as mass, damping coefficients, and spring stiffness often lead to less than optimal designs, highlighting the needs for computational approach to enhance the efficiency and performance. Okay, now let's move to literature review. The optimizing of suspensions has been widely studied. First, mathematical modeling. Bolke and Brookmans 2001 emphasized using second-order differential equations to model suspension system as mass springs damper systems. Hooke's laws provide the basis for minimizing oscillations. Second, balancing comfort and handling. Carlos Lopez Albert et al. 2022 demonstrates how multi-objective optimizations can balance comfort and handling through numerical simulations. They showed how stiffness and damping vary under different road conditions. The third one is adaptive suspensions. Basargans et al. 2030 explored modern adaptive system that adjusts in real time using electronic control units, enhancing performance beyond traditional mechanical designs. Okay, now this is the methodology. First of all, mathematical model formula suspension system is represented by the mass spring damper model, which is, you can see the model there, M equal to D power of 2 X over D of T power of 2 plus C dx over dt plus kx equal to ft. Here, M is the mass, C is the damping coefficients, and K the spring stiffness, and Ft the external force. Next, parameter selection. Realistic values for these parameters are chosen based on physical suspension data. The third one is solution technique. The differential equation is solved numerically using Mathematica as it handles complex scenarios effectively. The fourth one is simulation and visualizations. Displacement, velocity, and acceleration are simulated under various conditions, and results are visualized to evaluate the system performance. Now, let's dive into the computational aspect of the project, where Mathematica was used to solve the second order differential equation modeling the suspension system. The governing equation is m d power of 2 x over dt power of 2 plus c dx over dt plus kx equal to ft. This equation represents the system dynamics where m, which is mass of the vehicle, set to 1000 kilogram, c damping coefficient set to 200 ns over m, controlling how quickly oscillation decay, k is spring constants set to 15,000 n over m. Defining the stiffness of the suspension. Ft is external force model as 500 sin 2 pi t, representing a repeated bump on the road. So the step in Mathematica, first of all, defining parameters. Define m, c, k, and ft. So you can see at the slide. Next is setting up the differential equations. So there is the differential equations, and then defining initial condition, initial displacements, and velocity are 0. Solving equations, so we use that kind of equation in the Mathematica. Next, we need to visualizing the solutions, plot the displacement response over time. So as you can see there, they all are the Mathematica coding that I use. Next, so for the results, the graph shows initial oscillations that stabilize due to damping. Parameters like c and k directly influence how quickly the system returns to equilibriums, highlighting the importance of tunings for optimal comfort and stability. Using Mathematica simplifies the process of solving and visualizing complex suspension dynamics, providing insights for real-world applications. Okay, now let's move to the discussions. From the simulation results, we can make the following observations. Initial oscillations. After a disturbance, the system undergoes oscillation due to the interaction of spring and damping force. Damping effect, higher damping coefficients, which is C, reduce oscillations, improving stability but may compromise comfort. Stiffer springs, which is K, improve handling but leads to a harsher ride. Real implications, modern adaptive suspension can dynamically adjust parameter in real time, achieving an optimal balance between comfort and stability under varying road conditions. This ability makes them superior to traditional suspension systems. In conclusions, differential equations provide a powerful framework analyzing and optimizing car suspension system. Using tools like Mathematica, we can model and simulate suspension dynamics, fine-tune parameters, and design systems that deliver safer, more comfortable rides with continued advancements in adaptive technology. Future suspensions system will offer even greater performance and efficiency. That's all from me. Thank you.